Good everybody, this is CreamSpinachYo, and this is episode 9 of Math, Science, and Modern Warfare 3, and today we're going to hold off on the math for now, and we're going to talk about something really cool in physics. We're going to talk about the relativistic Doppler effect, and this is a very, it could be complicated if you don't have the proper math, but I'm gonna try to explain it to you as best I can. And this is going to be very, very cool, so let's get started. Now, in order to talk about the relativistic Doppler effect, we have to talk about the regular Doppler effect. And so, just to paraphrase it, if a wave source and a receiver are moving relative to each other, the received frequency is not the same as the frequency of the source. And just to be more specific on this, if they are moving closer together, the received frequency is greater than the source frequency, and if they're moving further apart, the received frequency is less than the source frequency. Now, there is a very, very simple example of this, right? Let's say you are standing on a sidewalk, and a car goes past you, and it's honking its horn the entire time, right? The pitch of that horn will change as it approaches you, then reaches your position, and then goes by you, right? And you know, it's the same thing for sirens. You know, anything where you are standing still and the source is moving relative to you, and it's emitting some type of sound. You know, the ice cream truck and that stupid song it plays does this. And the key for this is that this is valid only in the reference frame of the propagating medium. And we will talk, that is, you know, it depends on what reference frame you're looking at to determine if something is going to be a higher pitch or a lower pitch, and you know, we'll explain this later on. Now let's move on to the relativistic Doppler effect, right? So, unlike the Doppler effect, for light and other electromagnetic waves in a vacuum, remember, we're in a vacuum, a distinction between the motion of the source and the motion of receiver can't be made. And so, the Doppler effect will not work for light. And this is because in the first regular Doppler effect, we assumed that the time intervals in the reference frames of the source and the receiver were the same. Now, the reason why is because, according to the theory of relativity, again, this is a common theme throughout my physics videos, theory of relativity, the absolute motion cannot be detected, and that is according to the theory of relativity. And so, because of this, all observers will measure the same speed for light, independent of their motion relative to the source. And a common example is in the world of astronomy. We have something called a redshift, right? And redshift is observed in the light from distant galaxies, right? The galaxies are moving away from us, so the light they emit will be shifted towards the longer wavelengths, right? And it's called redshift because, guess what? The longest visible wavelengths that we can see appear as red. So that's why it's called redshift. Now, we do have, before I get started on an example, we do have two equations for this, and they are very specifically the same. Now, we have this equation, which I'm showing you right now, which is the equation if they are approaching each other, right? That is when the source and the receiver are moving towards one another. Now, this equation, the next equation, which I'm showing you right now, is when the source and the receiver are moving away from one another, right? And so the difference is, you know, the wavelengths are getting more chaotic, and the other one, they're getting more stretched out. That's the difference within, and the first one's called an approaching, and the second one is called a receding. Now, on to the example. Now, this is a I really like this example. So let's say you are traveling down a highway, or not a highway. Let's say you're traveling down a road with traffic lights, right? And you are speeding. And now you go over, right? And you run right through a red light. You speed past the red light, and it's a big problem. Now, the cop sees you and he pulls you over. What are you gonna say, right? Well, how about this? Let's suppose you say that the red light looked green because the car was moving towards the light, and hence it shifted the wavelength of the observed light, right? Oh man, that is pretty cool. Yeah, I tell you what, maybe you'll work on a cop, but you'll see what happens at the end of this example. Now, the idea behind this is that we can use our equations that I showed you before, and then that'll tell us the velocity, and then we need to find the frequencies of the light, and then we can make a guess for the wavelengths using c equals f lambda. I'm assuming you know that equation. That's equations for wavelengths, and we can determine the frequencies and figure out if you are right or not. So let's the observer, right? You were approaching the light source, right? So let's use that first equation for approaching the relativistic Doppler effect for approaching things. So we have this equation right here. Now, the next step, we're going to substitute c over lambda for f, right? And that's just an algebraic manipulation of c equals f lambda, right? And we get this ugly equation. Now, we are going to simplify this. So what does that mean? We're going to cross multiply, and we are going to substitute and then square. And so we will end up with this equation for that. Now what we're going to do is we're going to cross multiply, right? And we're going to solve for v over c, right? We need to know, we'll get the velocity, and we need to know the frequencies. So we do that, and we start off with the equation I'm showing you now. And so now what we're going to do is we are going to simplify and cross multiply. So we'll get lambda naught squared minus lambda prime squared equals all that lovely garbage. And look at that, we can cancel it, right? You can see that if we divide it, we can get v over c. And so we do that. And so v over c will equal 1 minus the quantity of lambda prime over lambda naught squared. And then the same thing in the denominator, but instead of a minus sign, it would be a plus. Now, the values for the wavelengths, for the colors that we can find, these I'm just gonna use two known wavelengths for red light and for green lights, right? And so for red, the color red will show at 625 nanometers or longer, and the colors green will show for 530 nanometers or shorter, right? So we put that into our equation, and we get that. We're trying to figure out the speed right here. So we get 0.848 as our answer, and then we're going to solve that for the speed needed to shift the wavelengths from 625 nanometers to 530 nanometers, right? And so we get 0.163. So now we need to solve for velocity, right? And so we substitute, we do all this lovely stuff, and in order for you to have a valid case, you would need to be traveling at 1.10 times 10 to the 8th miles an hour. So guess what? You were lying. You do not have a plausible case. But in the future, if you do happen to be traveling at that speed, your argument would work. So maybe, if you were around long enough for that to happen, keep that in mind. It might save you a hefty ticket. And so you do not have a case for this example. Now, you could be saying, well, Matt, well, duh, right? Cars can't travel at relativistic speeds, so the answer to your example is blatantly obvious. And guess what? You would be right. As of now, I do not know of any cars that can go that fast. So because of that, you're not going to have a case no matter what. Now, I think that would be it for this example. I think in the next episode, we're going to continue, we're going to build upon this notion, and we are going to talk about something very, very cool, and we are going to talk about clock synchronization and simultaneity. And I think that's a really cool idea. I think that's about it for this episode. Now, I want to apologize for my sniffing. I have a bit of a cold, allergies. You know, I got big time pollen problems. So every year, you know, every spring, summer, this usually happens. So again, I apologize. I hope that you were able to understand my voice the entire time, because I'm just gonna be sniffing like crazy for the next couple days. Well, weeks, maybe months, but we'll see what happens. If there's a cure for allergies, let me know in the comments. That'd be absolutely great. And like always, you know, if you really want to see something in this series, just let me know. We'll see what happens. Now, for the next episode about clock synchronization, it will be... I'm taking a risk, and I'm making it somewhat complicated. And the reason why I'm making it complicated, because I think it's a really, really cool... the example I have planned is very, very cool, and I'm really excited for it. So we'll see what happens. It requires me going on to Microsoft Paint and drawing a couple pictures, and needless to say, I hope it works out for the best. I'm trying to make it so I only need to talk about 1 or 2 equations to start off with in order to get this. And again, with this example, C equals F lambda, that's just the wavelength and frequency relation, so you can Google that. Anyway, thanks for watching. I really, really appreciate it. Feel free to subscribe to the channel and like the video. I do have a Twitter. Feel free to follow me at CreamSpinachYo. And I also have a PSN. If you really want to add me, feel free. Again, thanks for watching, and more importantly, have a great day.